Okay, hello everyone. Welcome to our Thursday afternoon seminar. Today it's a great pleasure to have with us Natalie Hogg from Paris-Saclay. So Natalie is an old friend of the Institute, and today she will tell us about the distance duality relation. Natalie, please, you have the floor.
Thank you very much. So yeah, it's a great pleasure to be virtually here back in Madrid. I suppose this would have been my hello and welcome to IPhT talk, but actually it's my goodbye, farewell from IPhT talk. So yeah, today I'm going to be telling you about the results from two works, one from a while ago and one more recently, both of which are on the theme of the distance duality relation, and in particular, how we can measure this thing, how it can be violated, and how the constraints that we can obtain on it could be biased in certain ways. So I've got two aims of this talk. Sorry, I'm just going to minimize the Zoom thing. There we go, so I can see my slides. Okay. So yeah, two aims that I want to achieve in this talk. The first is to show you how constraints on the distance duality relation, and I will define what this thing is in a minute, how they can be biased by modified gravity. And I want to draw an analogy here to the H0 tension and the supposition that the H0 tension could be caused by new physics. And the second aim of my talk is to use the validity of the distance duality relation, which I will show how we can measure this thing using late time data in a cosmological model independent way as a consistency check for beyond-LCDM cosmological models. So before I get into all of that, I want to sort of set the scene a bit. And I guess we hear more and more these days that we live in a golden age of cosmology. We're living in the era of precision cosmology. And people are talking about experiments like, for example, the dark energy spectroscopic instrument, which is measuring some, I don't know, millions of spectroscopic redshifts of galaxies. We've, of course, got the Square Kilometre Array, which is this huge array of radio telescopes that's going to be constructed in South Africa and will be a huge leap forward in, for example, 21 centimeter cosmology. And of course, everybody's delayed favorite delayed space telescope, Euclid, which may or may not launch at some point in our lifetimes, but when it does, promises to provide, really amazing measurements of cosmological parameters. So something that's been on my mind thinking about all of these wonderful measurements and all this great data that we're going to obtain in the next few years is this question of precision versus accuracy. And to illustrate what I am talking about here, I made this cartoon, which may be familiar to you from like high school science classes or something. And so on these dartboards, these are sort of representing some measurement that we want to make of a model or what we believe the truth to be, the truth about some physical law in the universe. And that's in the center of these dartboards. And the blue points are measurements that I'm making, by pointing my telescope at the sky, looking at some observable. And we might start off being in the bottom left corner here. So here our measurements are scattered kind of all over the place. There's a big spread. And so these measurements are both imprecise and inaccurate. We could maybe get a bit better at doing these measurements and end up in this bottom right panel here, where our spread is now much, much smaller. So our accuracy has improved and our precision is improved. And so we're now making measurements of what we believe to be the truth much better. Of course, we hope that we're always in this situation in the top right here, so where we're both precise and accurate. So our measurements are very nicely centered around this truth, the model that we're looking for in the middle here. And the error bar is really small, so the measurements we've made are clustered together. But what about if we're in the situation in the top left here? So our measurements are really, really good. The precision is amazing of this thing that I've measured, but it's very inaccurate. It's not at all centered on what I believe the truth about this model to be. And I think an archetypal example of this in cosmology is the H0 tension. So we have some measurements that we can make of this parameter H0, which necessarily assume a cosmological model. So they assume some kind of truth that we believe about the universe, and we believe it's described by lambda-CDM. And these are the measurements represented here in red. So from the cosmic microwave background, from baryon acoustic oscillations, and from weak lensing. But then we can also throw some darts at this dartboard and make measurements of H0 in a cosmological model independent way, for example, through Cepheid-calibrated supernovae and through strong lensing time delays. And of course, this is a famous tension that exists in cosmology. These two measurements don't match up, and they're different at the level of like 4.5 to 5 sigma. And so the question is, I mean, the sort of boring explanation for this kind of tension is that there's some systematic effect going on that we haven't properly accounted for. And in particular, in the case of the supernovae, people like to think a lot about whether the Cepheid luminosities could be incorrectly calibrated in some way, which leads to an incorrect derivation of H0 from the supernovae. But possibly a more interesting explanation could be that this bias is in some sense real, and it's caused by new physics. So again, in the example of the H0 tension, well, maybe if we want a larger H0 at late times, this means that we need some dynamical dark energy model, which is increasing our acceleration at late times and giving us a larger H0. And of course, yeah, this is the more interesting, in my opinion, the more interesting avenue to pursue. So now I want to think about whether there are other examples of this phenomenon occurring in cosmology. And that's what the first part of my talk is going to be about. So the fact that constraints on the distance duality relation can be biased by modified gravity. So now it's about time for me to tell you actually what the distance duality relation is. So it's this very simple relationship between luminosity distances and angular diameter distances. And they're related by this simple factor of 1 plus z squared. And you might think this is kind of a trivial statement to make, right? That measuring a distance to an object through one method should give me the same answer as if I measure the distance to that object through another method. But of course, this is cosmology. We're considering photons which are propagating and expanding space-time, and it's not necessarily so simple. So in actual fact, there are 3 specific conditions under which this relationship holds. So the first is that your space-time should have a pseudo-Riemannian metric. Now, the metric that we're probably almost familiar with in cosmology is the FLRW metric. So this has 1 time dimension and 3 spatial dimensions. So it's a Lorentzian metric. Pseudo-Riemannian metrics are more like the more general version of this Lorentzian metric. So you still have a splitting between your space and time dimensions, but you can have any number of spatial dimensions, any number of time dimensions. So this statement that space-time should be pseudo-Riemannian is, I think, not a controversial one. Although, of course, there are people that work on non-FLRW cosmology. The second condition under which the DDR holds is that photons should travel on null geodesics in your spacetime. So this is equivalent to saying that photons should be massless. And I think, again, this is not a controversial statement to make and a condition that we can well believe is valid in our universe. The third condition is the one which is easiest to consider violating, and that is that photon number should be conserved. So you can't lose or gain photons as they travel towards you. So how exactly does this lead to the DDR being broken? So imagine that you're looking at some luminous object like a supernova, for example, and maybe you have some cloud of dust in between you and that supernova. So the photons that are traveling towards you are getting scattered to dust, and the supernova consequently looks dimmer than it really is. So this luminosity distance will be larger than you would infer if there was no dust in the way. But if you were able to obtain an angular diameter distance to that supernova, so by looking at its angular size on the sky, well, angular sizes aren't affected by how bright or dim a particular object looks. They're the same regardless of its luminosity. And so consequently, you will measure a different luminosity distance than you would an angular diameter distance. And so your DDR would be violated. But maybe thinking about clouds of dust is not a particularly interesting avenue to go down. So we want to think of some more interesting mechanism through which the DDR could be violated and which we could then see how well we could measure this violation with current or future data. And in particular, in this work, we were interested in considering a mechanism through which photons can decay into axions, which are a hypothetical light scalar field, through interactions with magnetic fields. And so the question we want to answer is, if we're breaking the DDR via this photon decay mechanism, how well could we measure such a violation? So how precise are our constraints, and also how accurate are our constraints on this quantity. So a quick word about this model, this mechanism that we're using to get the photons to decay into axions. We simply have the observed luminosity distance being altered from the bare, or if you like, the true luminosity distance by this factor 1 over square root p of z. And this p of z function is given here. So the important parameter that we'll be focusing on is this capital A. You can think of this basically like the decay amplitude of this photon to axion decay mechanism. And so notice that if A is different from 1, then this P of Z is also different from 1. And so we have the observed luminosity distance differing from the true luminosity distance. So we have DDR violation. And apart from that, we have some other terms appearing here. So H0, the speed of light c, the co-moving distance dc of z, and this psi0 here. This term is related to the probability of a photon decaying into an axion over the length of its propagation. And we're considering cosmological scales here. So we just make the argument that the photon is going to travel a sufficiently large distance that it will, at some point in our huge population of photons, there will be a 100% chance that at least one of them will undergo this decay. So this, basically this psi0 becomes 1. So yeah, we're using the decay amplitude, this capital A, as a proxy for our DDR breaking. So we want to say, how well can we measure this quantity? So how are we going to do this? What observational data should we use? Well, for luminosity distances, the obvious answer is to use type 1a supernovae. And actually, we tested to see what would happen if we could just get constraints on this DDR parameter A with supernova data alone. But we found that there were some strong degeneracies appearing between the cosmological parameters and the DDR. So we need to add in another data set, and we added in baryon acoustic oscillations. Now these probe a combination of the angular diameter distance, the Hubble, actually this should say Hubble function, not Hubble parameter, and sound horizon scale. So these are obviously a great choice of data to use when we're trying to measure the angular diameter distance and the DDR. There's a couple of caveats. You need to assume a fiducial cosmology to obtain the angular diameter distance from the BAO to basically get rid of the dependence on h of z. And also, if you're considering cosmological models which are very different from lambda CDM, you need to start thinking about how the nonlinear scales in your power spectrum that are going to change your BAO should be modeled, which could be quite difficult. And then we thought, well, what other data could we possibly use? And we decided to think about something called standard sirens. So what is a standard siren? It's when you have a gravitational wave event with an observed electromagnetic counterpart. And why is this useful? Well, you can obtain a luminosity distance from a gravitational wave signal alone, but to do cosmology, you need a redshift as well. And so how can we get a redshift? Well, we need to be able to observe the galaxy that this event is in. And we can only do that if if the merging objects are luminous themselves. So you can't use black holes for this kind of thing, but you can use neutron stars. So standard sirens are effectively binary neutron star mergers for which we observe the electromagnetic counterparts. The problem is that we've only observed one of these ever, that was GW 170817. So using a single event, obviously, statistically speaking, is not such a great idea when you're trying to get reasonable constraints. So how can we utilize standard sirens in our analysis today? Well, the answer is, of course, we're going to create mock data sets and forecast constraints. So all the results I'm about to show in the first part of this talk are based on mock data. So they are forecasts for what we believe future experiments will be able to measure for our DDR violation. So what exactly are the mocks that we created? Well, we created an LSST-like, which actually is the Vera Rubin Observatory these days, an LSST-like mock of type 1a supernovae. This has 8,800 measurements of the distance modulus and consequently the luminosity distance up to redshift 1. We created a DESI-like BAO mock, which goes up to redshift 3.5. And then finally, a mock data set of 1,000 standard sirens up to redshift 5, based on the specifications of the Einstein telescope, which is a proposed next generation terrestrial gravitational wave observatory. Now, I think when I presented this paper in the journal club at IPHT, which was probably about a year ago or a bit more, someone said to me, oh, don't you think 1,000 events is a very optimistic estimate, even over the lifetime of the Einstein telescope, which might be 10 years? And the answer to that is yes, this is quite optimistic. And I said at the time that probably if we reduce the size of our mock data sets, the consequent effect on our results would just be that our error bars would increase, so the precision would be worse. But it's also an important point to make is that when we did this mock data set construction, we used what subsequently turned out to be a relatively naive prescription for the contribution of weak lensing to the errors on the luminosity distances in this mock data set. So actually we overestimated the weak lensing contribution to the error by quite a significant amount, particularly for the events at the higher end of this redshift range. So I would, if I was redoing this analysis, maybe I would decrease the number of events in the sample, but I would also correctly account for this weak lensing effect, which would reduce my errors. So I think the two things would probably compensate for each other. And this is a point where I want to do a short advert. So we discovered this lensing thing in the progress of another project, which I'm working on with basically many current and or ex-IPhT people, where we're forecasting the Einstein telescope's ability to distinguish between astrophysical and primordial black hole mergers. So yeah, I wanted to just advertise, we've got this code which we're working on, and it will be released publicly once the paper is ready, so hopefully in a month or so. And in particular, I wanted to highlight Francesca's contributions to this effort. An important factor in this work was modeling the merger rate of the astrophysical and primordial black holes, and Francesca has taken the lead on that. Okay, that's enough propaganda about future work. Now let's get back to the distance duality relation. So here's the first results I want to show. So I'm showing constraints on the matter density omega m, H0, and also our DDR violation parameter from these different mock data sets. So in red, I'm showing the combination of LSST plus Einstein telescopes, so supernovae and gravitational waves. In yellow, the combination LSST plus DESI, so supernovae and BAO, and then in purple, the full combination. And the main thing that I want to show you on this plot is the lovely precision we get on the measurement of our DDR violation parameter A when we have this full combination of data. So this is around about a 2% precision measurement on this quantity A. So we've answered the question, how well are we going to be able to measure this thing with these future data sets? But of course, it's not interesting to stop there. So what other things can we consider? Well, what we wanted to find out was what would happen if there was some, if you like, hidden modified gravity that we haven't taken into account in our analysis. How would this change our constraints? Would it change the precision, or would it change the accuracy in any way? So how do we investigate this? Well, we come up with some, it doesn't really matter too much what the specific model of modified gravity is. We have some generic theory in which we have a time varying Newton's constant. And we chose this because in such theories, you end up with a modified friction term, this is the friction term here, in your gravitational wave propagation, which is this. So in GR, this delta of tau is 0, but in these time varying Newton's constant theories, this is no longer 0. And the result of this is that your gravitational wave luminosity distance now differs from the bare one by this factor given here. So you can see this is going to lead to a DDR breaking in the gravitational wave sector. Now, an important additional point here is that in such theories where you have this time varying Newton's constant, it also alters the amount of nickel which is synthesized inside supernovae, which also changes the supernova absolute magnitude. So we include a correction for this also in our mock data. So what do? We recreate our mock data sets, but this time include these modified gravity effects. But we redo our analysis without taking those effects into account. So still, if you like, believing that we're in the true lambda CDM cosmology. And this is what we see. So in particular, first focus on the red contour here. So this is the combination of gravitational waves and supernovae. So if you like, where the most modified gravity effect is going to be seen. And you can see how this contour is now extremely biased away from, I hope you can see these thin lines, that represents the fiducial value of 1, is extremely biased away from that fiducial value. This is actually a 4 sigma false detection of DDR violation, and it's solely caused for by this modified gravity that we haven't taken into account. And the other important point to notice is that when we have this full combination of data in purple here, you can see that in fact the precision on this measurement is exactly the same as it was when we didn't have the modified gravity. So we're still measuring whatever it is we're measuring really, really well. But we have now this, this bias, this inaccuracy induced by the modified gravity. So how do we get rid of this bias? Well, it's easy in our case because, of course, this is mock data and we know what we put in there in the first place. It's a bit harder to do in real data, I think. But what we can do is reanalyze, allowing for this modified gravity. So we come up with some parameterization of our time varying Newton's constant, and which is given by this equation here. I mean, you could put, I think, whatever functional form you want here, it wouldn't make too much difference. And we repeat our MCMC sampling, now including this GA as a free parameter. And so this is what we come out. So here, what comes out, we can focus just in particular on the full combination of data again, so the purple contours. And now you see that having correctly accounted for this modified gravity effect, we now recover the true fiducial cosmology as we expect. And there's one last thing that I'll talk about in this first part of the talk, which is screening. So of course, we know that in modified gravity theories, where you have these additional scalar degrees of freedom, your scalar field can develop an environment-dependent mass. And so in regions where you're basically in high density or at small scales, your scalar field will screen out any effect of modified gravity. So for example, us here in the solar system, we won't observe any effects of modified gravity locally, but those effects would still be taking place on cosmological scales. So both supernovae and compact object mergers, so binary black hole mergers or binary neutron star mergers, these are both sufficiently dense environments that screening mechanisms would be present. But what would happen if only one of these two were screened? And in particular, what would happen if somehow the gravitational waves did not feel any screening mechanism, but the supernovae did? So we regenerated our mock data with this scenario in mind, where the supernovae no longer feel modified gravity, but the gravitational waves still do. So now we have one data set which feels no modified gravity, and that's in yellow, so the supernovae plus BAO, and the other two which feel some small effect of modified gravity due to its presence in the gravitational waves. So you can see that the bias on the DDR parameter is still there, so we're still detecting this false DDR violation in one data set, but in the data set without the gravitational waves, we now correctly recover the fiducial cosmology. So we believe that this is an interesting smoking gun for this, basically this kind of screening mechanism that you would see if you combine your data sets in these different ways. So this is pretty much just to flag up the point that it's always interesting to use your data sets separately as well as in a combined way. So obviously, if you're aiming for high precision, you want to combine your data sets. But to uncover subtle effects like this, which could be caused by screening, by modified gravity, it's important to also use them separately in your analysis. So yeah, this is the conclusions from part one then, that constraints on the DDR could be unexpectedly biased if you assume the wrong fiducial cosmology, but that your constraints will remain just as precise as in the non-biased case. So it's not immediately obvious that you've done something wrong because your precision is still good. And lastly, that this screening and mechanism, let me start this sentence again. Lastly, this effect that we get from having one of the objects, so the supernovae, being screened, but not the standard sirens, could end up being a smoking gun for modified gravity with this particular screening mechanism. And I will admit it's a bit of a toy model, but I think still a good example to show. Okay, so second part, and this part is a little bit shorter, I think, than part one.
Sorry, Natalie, there is a question by Santi.
Go ahead.
If I can ask to conclude this part. So I think you said this at the beginning, but so what would be the natural way to produce this duality relation broken? Because I would have thought that precisely modified gravity would be one, or so is that a bias, or is it that, I don't know, somehow detection, or what other mechanism do we expect that could create this DDR?
Yeah, so I think it's pretty much anything that you could think of where you are losing photons somehow. So whether it's this decay mechanism or, I mean, off the top of my head, actually, I can't think of anything in particular, but yeah, well, okay, so you have the two different effects, right? You have one where you're breaking the DDR in the electromagnetic regime, and for that, you should be losing photons. The second, where in these modified gravity theories, you are changing the gravitational wave luminosity distance. And I guess, I mean, here we just considered these theories with the time-varying Newton's constant. I'm guessing that there could be other modified gravity theories which would produce the same effect. And your question, is this a bias or is this a detection? I mean, it's call it what you want. Yeah, if you're a modified gravity person, I guess you'd say, oh, look, we've detected modified gravity. But if you're trying to analyze, I don't know, you're just cosmological parameters and you think you're in lambda CDM, you would identify it as a bias, I think.
Okay, thanks.
Cool. Are there any other questions before I carry on? Okay. So yeah, part 2. Is the DDR consistent with beyond lambda CDM cosmological models? So what I'm doing in the second part of this talk, I want to forget all of the discussion that we've just had about forecasting and about mock data. This is all going to be based on real data that's currently available. So this is all, if you like, real measurements. So what I'm aiming to do here is measure the DDR using a collection of late time data and show that it's valid. And I want to avoid any dependency on a cosmological model in doing so. So I'm going to parameterize the DDR in this way. So I've just divided both sides by 1 plus z squared dA. And I end up with this function eta of z. And if eta of z is different from 1, this is going to indicate a violation of the DDR. Now, I do a little bit of algebraic manipulation of this expression just to show you how the different probes, how the different observables are going to be used to constrain this function, or in fact, a parameterization of this function. So what we have from the standard candles, so the supernovae, they are actually measuring this combination H0 dl of z. From the standard rulers, as I mentioned before, you don't measure dA of z by itself, you actually measure it in combination with h of z. And this is normally where the cosmological model will come into play. But to avoid this dependency on the cosmological model that we want to do here, we introduce a third probe, which we call standard clocks, or they're otherwise known as cosmic chronometers. So exactly how does this work? Well, you aim to identify certain galaxies for which you can measure both their age, so their physical cosmic age and cosmic time, and their redshift. And in so doing, you can construct a ratio of changes in redshift to changes in time, if you have a large enough population of these galaxies. And this ratio, which is tends to dz by dt, is proportional to h of z. And so consequently, I've got a more detailed slide at the end if you want to see more details about this, but consequently, you can measure h of z in a cosmological model independent way from these cosmic chronometers. So using these 3 data sets, we're able to constrain H0 and a parameterization of this function eta of z. So this is shown here in this red term here. So really the results I'm going to show in a moment are constraints on this epsilon. So if epsilon is different from 0, eta of z is different from 1, and the DDR is violated. And I also want to make the note that we checked for, I think, about 10 different parameterizations of this function eta of z to make sure that our results were stable. And indeed, they really didn't change with these different parameterizations. So here's the results which we obtained using this collection of late time data. So remember, the question we're now trying to answer is the DDR valid at the moment? So is there any photon decay? Is there any modified gravity, anything like that? And the answer, maybe unsurprisingly, is there is not. So we measured epsilon to be 0.001 plus minus some small amount. So we can basically consider this to be 0. So at least from this collection of data sets. So yeah, I should say this is using the Pantheon supernovae, SDSS BAO, and then a collection of cosmic chronometers. So then what we want to do is, having now established that the DDR is in fact valid at late times, at least up to the redshifts, the maximum redshift we have in this collection, I think is something like 2.5. We can use this as a consistency check for beyond-LCDM cosmologies. So exactly how do we do this? Well, so yeah, our late time data is implying that epsilon equals 0, eta of z equals 1, without assuming a cosmology. So now what we can do is think of some extended cosmological models and use a separate data set. So we use the Planck likelihood to obtain constraints on H0 in those models. So then, having fixed H0 in these extended cosmologies, we simply use that to infer what epsilon would be in those models and see if that's consistent with our expectation that eta of z equals 1. So as a visual example of what I'm talking about, let me show you here. So this is answering the question, rather than an extended cosmology, just a separate measurement of H0. So is the DDR compatible with the reset out, so the Cepheid-calibrated supernovae H0? So the blue contours here, excuse me, are exactly what I was showing you just now, our results with the Pantheon, supernovae, SDSS-BAO, and cosmic chronometers. And then what we do, so firstly looking at the red contour, is we have the measurement of H0 in lambda CDM from the Planck likelihood. And then we simply reweight our contours, our results, in fact, our MCMC chains using this H0. So we're, if you like, fixing the H0 and therefore inferring what the epsilon should be. And you can see, hopefully you can see this thin line crossing here. The result is perfectly consistent with epsilon equal to 0. We can now do the same thing with the reset al H0. So you know this is the one which is, you can see it's in tension with the Planck one. And now we infer, well, now we can see that this contour is just crossing the this line is just crossing the 2 sigma region of this contour. So I obviously don't want to make any bold claims or say anything, you know, too strong here, but I think it's interesting to notice that this is a sort of a curiosity, if you like, that the reset out H0 is not in perfect agreement with our expectation that the DDR should be valid at late times. And you can imagine, you know, maybe a few years down the line, we get another H0 measurement, which is on the high end, so around 70 kilometers per second per megaparsec, but perhaps with improved precision. So this contour is a little bit smaller. And then we would be seeing not only a tension in the H0 values, but also a tension with the fact that we expect the DDR to be valid at late times. So this is an interesting point, I think. So now we can basically do exactly the same thing, but testing some different cosmological models. So as I said before, what we do is obtain constraints on H0 in these different cosmologies and then reweight our results to infer what epsilon would be. And so I'm showing a selection here in the paper. We actually tested a few different combinations of these things. These are just to give you a flavor of the results. So the orange bar down here, this is the lambda CDM one, so the same as the red contour, which I already showed you in the previous slide. Then we added the possibility for having massive neutrinos. We investigated the possibility of additional relativistic degrees of freedom. We added the possibility of additional spatial curvature, and then we added all of these 3 things together. And so what you can see is if you have lambda CDM plus massive neutrinos or extra degrees of freedom, the epsilon that we measure in these extended cosmologies is consistent with our late time expectation of the DDR being valid. However, in the case where we've added spatial curvature, this is actually now, well, again, I don't really want to call it a tension. This is actually about 1.6 sigma or something like that, different from our expectation that the DDR should be valid. And we see the same thing where we have these, where we have the spatial curvature, the massive neutrinos, and extra degrees of freedom. We see a little bit of discrepancy with epsilon equal to 0, though in this case, this is being purely driven by the spatial curvature.
Sorry, Natalie, question.
Yeah,
so in this case, how does the curvature affect the DDR? Because the curvature should be included in the definition of the distance, right?
Yeah, so
the main effect comes from the peaks of the CMB somehow?
No, I think it's actually driven through the result that you get for H0. You can basically see it, well, even, where's the plot gone? Yeah, this plot. because what we do is obtain the H naught that you expect in that cosmology and then use that to get epsilon. So if the H naught is, on the low side, the epsilon will be larger, and that's consequently where the
so it's due to the degeneracies then.
Yeah, exactly. Yeah.
The curvature. Okay, thanks.
Okay, I don't think I had anything else to say on that slide. No. Are there any more questions at this point? Okay, well, I'm pretty much finished, and unfortunately a bit ahead of time, unexpectedly, but that will leave some time for questions, I hope. So yeah, and the first aim of this talk was to show you how constraints on the DDR could be biased by modified gravity in an analogous way to how the H0 tension is speculated to be caused by new physics, and I hope I showed you that. And secondly, to use the validity of the DDR at late times as a consistency check for beyond-LCDM cosmological models. And I want to point out again the two papers where we've got more details of basically everything that I've talked about, including the details on how we created the mock data, the details in the second paper about the data we used, and more of the consistency checks. So yeah, thanks very much for listening, and I look forward to your questions.
Okay, thank you, Natalie, for this very nice talk, very interesting. So we have ample time for questions and comments from the audience. Sachiko, yes, please.
Yeah, thank you, Natalie. Sorry, I have noise around. So, is it which is more important for gravitational waves to have a high redshift event or more numbers nearby?
Sorry, can you repeat is it more important to have something? I didn't catch that.
For gravitational wave events, is it more important to have a high redshift event or nearby, more number of nearby events?
Okay, okay. So is it more important to have high redshift events or a larger number? So I guess it depends on what you want to do. I think, well, I can answer the question from the perspective not of this work, but of the one that we're working on in terms of the distinguishing the astrophysical and primordial black holes. In that case, it's more important to have very high redshift events, because we expect that due to how the merger rates of the two objects behave, that the ABH merger rate will fall off at high redshifts, whereas the PBH one continuously increases. So you expect if you get to a sufficiently high redshift, an event you observe will be a primordial black hole with obviously some uncertainty. But for analyses like this one, where we're mostly interested in late time, then I suppose having more at lower redshift will be more useful for this, just to improve your precision. But of course, in a perfect world, we would have loads of events at every redshift, right? So we could do what we wanted. So, yeah.
Thank you.
Okay, any more questions, comments? Okay, I have a quick question. So in the second part of the talk, you said you used the cosmic chronometer data. Mm-hmm. So is this a compilation by Moresco et al?
Exactly, yeah.
So recently there was a new paper by Moresco, maybe like 2-3 months ago, I don't remember exactly, maybe just a bit before Christmas. Mm-hmm. And they did summary analysis of the data, and they found like the errors increase substantially. So do you know if this would affect the results, and how would it affect the analysis?
Yeah, that's a good question. So I think that was almost around the same time that we put our paper out. We had some discussion in the appendix of our work, which was about some of the systematics associated with these things. And in that case, we found there was little effect. But if their error bars have significantly increased, then yeah, I think it would. I mean, well, let me find a plot. I guess any of these plots. It would only serve to basically blow up this contour a bit. I'm not sure. I guess it would be more interesting if it, shifted these numbers, if it was suddenly, with their new findings, epsilon was no longer 0, but yeah. I guess that's unlikely, although it's something that we should check, I think. Yeah,
if I remember from that paper, they say that this new analysis just increases the systematics, which increases the total error. So my impression is as well that it would probably just increase the contours.
Yeah.
Hopefully.
Always the way.
Yeah. Okay. Any more questions, comments? Okay. If not, then we can thank Natalie again. Thank you again, Natalie, for this
Thank
very
you.
nice talk.
Thanks for having me.
Thank you.
Oh.